This is problem 14 of chapter 20. What we have is another one of these studies by the National Center for Education Statistics, and this time they're asking students if their mothers had graduated. And in 1996 that number was 31%. So they want to know if things have changed. So in 2000 they did a survey, and from a large survey, and they have 32%. So they want to know if that's statistically significant. So is there evidence of a change? So that's what we want to prove. So I guess I'm going to actually cheat, so to speak, and do the alternative hypotheses first. So let's just say the percentage of percentage of students in 2000 whose mothers had graduated from college is different than 31%. Okay, so that's going to be my alternative. Let me put that, move that over here, and it looks like I'm going to need, that should be then. So let me just do a carriage return. And so formally we're going to say P is, I'm going to have to write it out, not equal to 31%. Okay, so again, if you look at the question, it says, is this evidence of a change? They didn't ask, has it increased? So this is going to be a two-tailed test, because we're saying not equal to. All right, so my my null hypothesis would be that it hasn't changed. So the percentage of students in 2000 whose mothers had graduated from college is 31%. So P equals 31%. And once again, I need to do some kind of, no, I guess it'll fit. Okay, so those are the hypotheses. So let's check the conditions real quick. So I think it is reasonable to assume that the decision of one student's mother to go to college and graduate is independent of another student's mother deciding to go to college and graduate. Okay, so that's the plausible independence. So let's see. Need to go up a little bit. Need to go up further. Okay, so just to save time, that's good enough for now. Let's see, random sample. Although not specified, we can assume, because it's an organization, it should be trustworthy, right? Assume that the national, the National Center of for Education will use random sampling methods. I think it's reasonable. So here we don't have to justify that it's representative. We can just assume that it's going to be random, because we know a professional organization will do that. Okay, so I'm trying to zip through these as fast as we can. Let's see. The 8,368 sampled students is less than all students in the U.S. Okay, so that should be pretty straightforward. So all we need to do now is check the sample size. So I'm going to switch over to my electronic pen. So the sample size was 8,368. So we're going to have 8,368 times 0.31, and that's equal to 2594.08, and in 8,368, no, my bad, yeah, that's it, but it's times 0.69, right? 0.69, and that's also going to be a pretty big number. 5773.92. So both are greater than 10. So the sample is large enough. Terrible. Large. Okay, so the conditions for inference are met, so we can proceed with the normal model to perform a z-test, and it's this time it's going to be a two-tail test. Okay, so the mean, I should put a hat right here. So what we're doing is we have p hat. This is this p hat, and if we didn't have this thing here, it would be kind of like, you know, we could, if we did multiple samples over and over again, we would build our own distribution, but we don't have time to do that. That would take forever, probably. So instead we're going to make a model. So it's p hat. So the center is going to be 0.31. Okay, 0.31, the hypothesized value. So this model is exactly what we hypothesized. So this is going to be the square root of 0.31 times 0.69 divided by this very large sample size. So you can suspect a very small standard deviation. In fact, it is very small, 0.0051. Okay, so for our model, our standard deviation is 0.0051, and our center is at 3.1. Okay, so you don't have to label the tick marks, but let's see what. So the sample statistic was what did we have? We had, oh, they didn't say. They just, well, you could figure it out, but it's 0.32. Okay, so they didn't tell us the number of successes, but it's 0.32. Alright, so that's going to be a little ways off, I think. It's going to be out here somewhere. Not sure just yet. So let's calculate the z-value. We're going to have the observed value is 0.32, and we're going to subtract off 0.31. We're going to divide by this very small standard deviation. Okay? And so we get a z-value of 1.978. So I guess I was wrong a little bit. It's p hat is right there. Okay, so p hat is equal to 0.32. Alright, and we want to find that area under the curve, and that's on the normal model, that would be 1.978. Okay, so we want to know the probability of this, but it's a two-tailed test. Okay, so we said not equal to. So what we have to do is we have to go over here and we have to find the sum of this area and that area. So the p-value is both. It's the sum of both, because it could be over here. I will try to explain this in class, but right now, trust me. Okay, so we're going to have to, the p-value is going to be 2 times the probability of p hat greater than 0.32, and that's going to be 2 times the probability of z greater than 1.978, and so that's going to be 2 times the probability, or the normal CDF of 1.978 out to infinity. So all we're doing is finding the area over here, and then we're just doubling it because the normal model is symmetric. Okay, and if you use your calculator, you should get something like this: 0.048. Okay, 0.048. Okay, so approximately 4.8%. So that's pretty small. Okay, so this difference, this deviation of 2 standard deviations away from the mean, could be due to more than just random sampling. It could be that more women are getting college degrees. Okay, so what we're going to say is the p-value is small. So we reject the null hypotheses. Now you don't have to restate it, because what we want to do is state our conclusion. Our conclusion is there is sufficient evidence to what do you want to say? To suggest that the percentage of students, and if you get lost, you can just come up to here and say the percentage of students in 2000 whose mothers had graduated from college is, okay, so suggest that the percentage of students in 2000 whose mothers graduated from college is greater than 31%. Okay, so that's proof that it's different. Now, for those of you who are watching this, you're going to have a little advantage over the students that don't, because I haven't said yet, but when you reject the null hypotheses, this is great for saying, okay, we have evidence, but what do we think it is? So whenever you reject the null hypotheses, oftentimes it's not a bad idea to then compute a confidence interval. You don't have to recheck the conditions. You've already checked them. So you just take p hat, decide what confidence you want. Okay, so you could be 95% confident, and then of course you would use 0.32 and 0.68 instead, but you'd still use the same sample size, 8368. So you could calculate that confidence interval and say this is what we think it is, and I'm sure you would find that that confidence interval is greater than 31, but not by much. Okay, so there was one follow-up question on this problem. It's not that big of a deal, but just I think they wanted to drive the point home. Do you think this difference is meaningful? So there's a difference between statistically significant. Statistically significant means that the difference from the hypothesized value is so great that it probably has something to do with more than just random sampling. However, if you were doing a study and after the work all you found was a 1% difference and you wrote a report, I don't think that would be very interesting to people. And so it's probably not a very meaningful result. That's all that question's getting at. All right, so that's problem 14, chapter 20. Good luck.